Monocular human pose and shape estimation is ill-posed, since multiple 3D human reconstructions can explain a given 2D image. Thus, recent methods predict a probability distribution over simple pose and shape parameters, but exhibit a trade-off between three key properties, namely consistency, diversity, and accuracy. In particular, it is challenging to model a distribution over a diverse range of 3D solutions that are all consistent with the visible cues in the 2D input. HuManiFlow aims to overcome this trade-off. We use normalizing flows that are explicitly pushed onto the SO3 manifold of body part rotations and autoregressively conditioned on ancestor part rotations to learn expressive yet input-consistent pose and shape distributions. These prove to be useful in downstream tasks, for example as an image condition prior doing model fitting. Let's take a closer look at the metrics we use to evaluate pose and shape distribution predictions. In terms of sample input consistency, sample diversity, and distribution accuracy, the match between predicted samples in the input image is measured using the average reprojection error between predicted 2D key point samples in the image plane and ground truth 2D key points that are visible in the input image. The diversity of 3D pose and shape samples is measured using the average 3D Euclidean distance of predicted key point samples from the sample mean. Occluded or depth ambiguous key points should exhibit greater 3D diversity. In addition, we visualize sample diversity using the variance of 3D body vertex coordinates along the x, y, and z axes, where the z-axis corresponds to depth perpendicular to the image plane. We expect to see greater 3D variance along the depth direction and for occluded vertices. We measure distribution accuracy using a proxy metric, 3D key point error, or MPJPE, computed using the minimum error sample out of n predicted 3D samples. N is increased from 1 to 100. If the ground truth pose and shape has high likelihood under the predicted distribution, we expect the minimum MPJPE to improve quickly with increasing n. As mentioned in the preview, current approaches to probabilistic pose and shape estimation exhibit a trade-off between these three metrics. Here, we discuss three such approaches. Some yield pose and shape samples that closely match the input image, but fail to model a diverse range of plausible 3D solutions, as shown by directional variance visualizations. Others generate diverse samples, but do not consistently match the input image. We suggest that the lack of diversity may stem from the use of distribution models with limited expressiveness, and non-probabilistic losses between 3D point estimates and the 3D ground truth. A lack of input consistency may arise from not modeling the manifold of human pose and accounting for the structure of SO3, the space of 3D body part rotations. The hierarchical structure of the human skeleton should also be considered. HuManiFlow aims to address these shortcomings and yield simultaneously consistent and diverse pose and shape samples. We use the simple body model to parameterize body shape and pose. Our aim is to predict distributions over simple parameters conditioned on an image. Pose is defined by the 3D rotation of each body part in the simple kinematic tree about its parent joint. Body part rotations lie on the SO3 manifold. There are many ways to represent these rotations, such as matrices or axis angle vectors. The relationship between these in Lie theory will be used for our pose distribution predictions. Simple outputs of vertex mesh given an input shape vector and 3D body part rotations. We use normalizing flows for distribution prediction. These model complex probability distributions by pushing a simple base distribution through a bijective differentiable flow transformation. The density function of the transformed distribution is obtained using change of variables. In practice, the flow transformation is the composition of multiple bijective neural networks. We want to use normalizing flows to model distributions over simple pose parameters. This entails defining flows over the non-Euclidean domain SO3. SO3 is the Lie group of 3D rotations. The corresponding Lie algebra consists of skew-symmetric matrices, which have a one-to-one correspondence with 3D Euclidean vectors. The exponential map from Lie theory transforms a skew-symmetric matrix to a rotation matrix, and is given by the Rodriguez rotation formula. The skew-symmetric matrix can be decomposed into a scalar angle of rotation and a unit vector axis. Thus, the exponential map links axis angle vectors to rotation matrices. Note that multiple axis angle vectors can map to the same 3D rotation. We ultimately aim to learn expressive probability distributions on SO3 using the method of Falorci et al., who construct a distribution over axis angle vectors corresponding to Lie algebra elements and push this through the exponential map using once again the change of variables formula to give the probability density function. The non-bijectivity of the exponential map is handled by summing over all axis angle vectors that map to the same 3D rotation. To avoid an infinite summation, the axis angle density function can be defined with compact support. We used normalising flows to learn axis angle density functions. Given an image, we first compute an input proxy representation, which is passed through a CNN encoder. Our method outputs a joint distribution over simple pose and shape parameters, which is factorized into a Gaussian shape distribution and a full-body pose distribution conditioned on shape. Full-body pose is further factorized into per-body part rotation distributions, which are autoregressively conditioned on ancestor body parts along the kinematic tree. We use normalizing flows over SO3 for per-body part rotation distributions. Flows are conditioned using a context vector, which is computed as a function of input features, shape, and ancestor rotations. We train our model using a negative log likelihood loss, as well as a 2D key-point sample reprojection loss. We avoid using non-probabilistic losses, such as mean squared error between 3D ground truth and a point estimate prediction, since the ground truth is but one of many plausible 3D solutions. Applying this ill-posed loss reduced 3D sample diversity. Compared to other probabilistic methods, HuManiFlow yields samples with lower 2D reprojection error, while maintaining 3D diversity. It also results in better minimum sample MPJPE, and a faster rate of improvement with increasing number of samples, implying a more accurate distribution prediction. When used as an image condition prior during model fitting, HuManiFlow improves 3D accuracy over other probabilistic methods, suggesting that consistent, diverse, and accurate distributions are better for downstream tasks.